Hi everyone, my name is Hector Gomez.
I'm Oscar Balvanera,
Fernando Casas.
and this is our 157 design project where we designed a pneumatic hole punching system.
The motivation and purpose for the pneumatic hole puncher is methods out there right now for sheet metal are difficult and expensive. Also, inefficient solutions are heavy, costly, and manual labor intensive. We designed a QFD for our project, mainly focusing on several areas. To punch a hole with 2,000 pounds of force, cost, how fast it is, the size, the weight, and having a compressor of 150 psi. The customer requirements for our projects is the system to be economical compared to similar systems, the system to be compact, easy to operate, versatility in function, and cut holes of accurate size with precision.
Existing methods of punching holes in sheet metal often involve various parts, are expensive, or require a lot of user input. One of the products shown is a handheld sheet metal punch. This requires a lot of force input from the user, and it also neglects accuracy and repeatability. Another product available is a pneumatic system, which is heavy and expensive and difficult to transport. One of the most economical ways of punching a hole in sheet metal is with the use of a hammer and center punch. This would require a drill bit to drill through the sheet metal and create the hole. Similar to the handheld punch, this suffers in loss of accuracy and precision.
We chose a double-acting pneumatic cylinder for our project since it is able to produce an output force in standing and retracting directions. The double-acting pneumatic cylinder has a bore diameter of 4 inches, a rod diameter of 1 inch, and 2 inches in length. This pneumatic cylinder will help achieve our design specification of 2,000 pounds and perform a shearing operation under 3 seconds. Doing a few calculations, pressure times area at different air pressures, we were able to determine 150 psi is sufficient to produce 1,885 pounds of force to punch a hole on the sheet metal. Also, since the compressor maxes at 150 psi. Since we assume 1 cycle per second, we were able to determine the volumetric and having a speed of 2 inches per second when punching the hole to the sheet metal. Furthermore, this resulting in having a travel time of 0.6 seconds to when it makes contact with the sheet metal to pierce a hole.
The pneumatic cylinder bracket is designed to be made out of 6061 aluminum. We decided the most efficient manufacturing process to manufacture this is forging. By isolating the pneumatic cylinder base, we are able to perform a simple yet effective analysis using SolidWorks simulation. By using advanced constraints, we are able to accurately simulate bolts holding the base of the cylinder support. This allowed us to perform a remote load at the piston location. Here we are seeing the factor of safety distribution plot across our system, and the most critical component prone to failure is at the top right next to the piston cylinder. The factor of safety at this location resulted in 2.3. The resultant von Mises plot displays our maximum stress being 17 ksi, which is significantly less than the yield strength of aluminum at almost 40 ksi. The pneumatic hole puncher is designed with a chain and roller system to feed flat sheet metal stock through the rollers and position it under the cutting bit. Once positioned, the user can actuate the pneumatic cylinder to punch a hole through the sheet metal at a high force. This is done remotely and results in a safe and highly efficient method of punching holes through sheet metal.